Hello students, this is a Common Core Geometry video review of the problem sets from Unit 5. I'm taking a look at the first 5 problem sets to prepare you for the first quiz in Unit 5. And remember, this unit is all about proving two triangles congruent. This is the first problem set. Hopefully you attempted it first before you're taking a look at these answers. So if you haven't, go ahead and pause the video and then I'll give you answers in a moment. Alright, looking at question number 1, you can see that this point translated to this point down here. The first thing that you should observe is that it is a rotation of 180 degrees, right? If you draw a line from here to here and then a line from here to here, that's going to be a straight line, 180 degree rotation. However, it's not about the origin. It's not around the origin. It's around this point, which is 0, 2. 0, 2 is the correct center of rotation here, but a clockwise rotation of 90 degrees isn't going to do it. 90 degrees is going to put it up here, not over here. For letter C, we took a look at it, but it looks like that those transformations make it into -3, -10, so that's not going to do it either. Those translations down here, a reflection across the y-axis, which means the x value changes, and then a reflection across the line y equals 2 means we count the spaces between 2 and 8, the y value, and then we go the same distance the other way. So that's a distance of 6. We go downwards by 6 to -4, and we can see that that is the point that we found here. So that's choice D. For question 2, it states that these shapes are congruent. It asks which is not a way of transforming M into M prime. A rotation of 180 around the origin, that would do it. It goes from here to here. And then this point down here becomes this point up here. A reflection across the X and then a reflection across the Y. That is a reflection across the X, which would be here, and across Y, which would be here. A reflection across Y would bring it here. However, a translation down 2 units is not enough to bring it from up here to down here. I'm going from this point down 1, 2, 3, 4, 5, 6, 7, 8, going down 8, right? So down 8 units would be a correct translation. And then a translation right of 10, well, from here to here, it is to in the x direction over by 10. For question 3, it is a reflection across the y-axis. Reflection across the y-axis means we change our x value. Very straightforward. And here it's a reflection, wow, across the x-axis, which means we're changing our y value. That's this one. All right, in question number 5, you can see that B and F are congruent, and BA and FL are congruent also. It asks us which will prove that BAT is congruent to FLU. And when I look at the diagram, I see that if this angle is congruent to this angle, we have angle side angle. That's one of our 4 shortcuts for congruence. That means it's choice A. For question 6, I know that these two triangles are congruent to each other. It says it right here. And order is critical, which means A and X correspond. In other words, angle A is congruent to angle X. Angle C is congruent to angle Z, and so on. Order is critical when we're talking about congruent statements, which this is, a congruent statement. Which statement must be true? Well, I know that A is the first letter here. X is the first letter here. That may seem trivial, but in geometry, when you write a congruent statement, order is critical, which means the letters are in the correct order. They all correspond to each other. For question 7, two triangles are congruent if, we talked about this at the beginning of the unit, the corresponding sides and the corresponding angles must be congruent. Letter A is not correct because it's possible to have corresponding angles that are congruent, but the triangle might be many, many times bigger. The angles in each triangle have a sum of 180. Well, that's true, but it doesn't necessarily make them congruent. That just makes them triangles. And then for letter D, corresponding sides are proportional. That makes them something else, similar, which we'll talk about later. For question 8, if two triangles are congruent, all of their measures must be equal. But this specifically asks about a right triangle, which has a 90-degree angle, and an equilateral triangle, which doesn't have any 90-degree angles. If those two angles aren't the same, that means the triangles are not equal. Take a look at lesson 2 problem set. I will give you a moment to finish it, and then I'll show you the answers. All right, in question number 1, it says Sss Congruence Axiom, which is another way of saying Sss postulate or Sss theorem. It says two triangles are congruent when 3 sides of one triangle equal blank of the other triangle. That blank should be 3 sides. Here it says in two triangles, if 3 pairs of sides are equal in length, then the triangles are congruent. That, of course, is side, side, side. For question 3, it gives you this situation and asks for the most direct method of proof. Direct methods of proof mean methods that are very straightforward, and side, side, side is equal to side, side, side. That's very straightforward. We're not able to use this one yet because we haven't even gone over this, and all of the other ones involve angle measures. For question number 4, it should look very similar because we literally just did it. On to questions 5 and 6. These are the first couple of proofs that I asked you to do alone by yourself. I'm going to allow you to pause the video and then I'll give you some examples of correct answers. All right, take a look at these two proofs. In these two proofs, we're trying to prove side, side, side is congruent to side, side, side. Both of them use that shortcut because that was the shortcut that we taught here in lesson 2. A couple main differences. This one says BD bisects AC, so we're using the definition of bisector. Here it says that C is the midpoint, so we're using the definition of midpoint. And again, here we use it twice. In both cases, we get 3 pairs of corresponding sides is equal to 3 pairs of corresponding sides, or congruent, I should say, which means that the triangles are congruent to each other. All right, moving on to the problem set from lesson number 3. Hopefully you tried this yourself, but if you didn't, please pause the video for a moment, try it out, and then I will show you the answers. All right, for lesson 3, all of these answers were side angle side, but I just want to walk you through exactly how. We were given parallel, so again, we mark parallel lines with this little arrow. We spoke about this in class. And we were also given that these 2 line segments were congruent. Same thing with these 2 line segments, they were congruent because C is the midpoint of AE. One thing that they didn't give us was this angle here, which would be very helpful, but they said parallel, which means alternate interior angles are congruent. So we were able to use side angle side. Again, alternate interior angles. For question 2, we knew that these 2 angles were congruent, and the reason for that was just vertical angles. So now side, angle, side is congruent to side, angle, side. It gives us all the information we need. The accompanying diagram, isosceles, was the tricky part here. Isosceles means these 2 sides are going to be congruent to each other. ACB is bisected by CM. That means that these 2 angles are the same, and we're using that reflexive property again to say that this side is congruent to itself. So side, angle, side. For question number 4, hopefully this is getting familiar to you because you've seen it 2 other times so far this video. Now take a look at the proofs, pause the video, try to see if you can get them, and I will show you the correct answers in a moment. All right, both of these were straightforward SAS postulate problems. It asks us to write the givens first, so we do that. That's kind of like our introductory paragraph. Here we have one of the sides. Then we have an angle that's in between them. That angle is there because of a definition of bisector. Notice we have bisect here. And then the last part is the side. Here we use reflexive property because this side is shared between 2 triangles. Shared means reflexive. For number 6, it was a slightly longer proof, but we were still able to do it in less than 10 steps. We had this given, AB and DE is given, so that's going to be one of our sides. ABC is congruent to EDC because of alternate interior angles. Again, we have 2 parallel lines here and here, and the transversal BD between them. That is our angle statement. And then BC is congruent to DC. BC is congruent to DC here because of the definition of midpoint. Notice that in the givens, it gave us midpoint. All right, so those are 2 fairly straightforward SAS postulate questions. Let's move on to the 7th and 8th question in the problem set. Pause the video, try these, and I will show you the answer. All right, here's question number 7. Amazing what you can get from just one given. It says that O is the midpoint of MP and NQ. MP is split in half, which means MO and OP are congruent. NQ is split in half, which means NO and OQ are congruent. And then we have MON and POQ are congruent based on vertical angles, which means we can safely say that MON is congruent to POQ. Notice one thing. In this situation, we had this S, this side, and this side as well. And this angle, even though it's not in the same order as SAS here in the statements, that's okay because when you look at the triangle, we have a side, another side, and the included angle. As long as we have 2 sides in the included angle, we can still say it's side, angle, side. If we have 2 sides and a non-included angle, it's not going to work. That is an illegal shortcut. Taking a look at number 8, pause the video, try to write it out, and I'll show you the correct answer. Here you can see the answer for question number 8. It claims that there's a perpendicular bisector here, which means I can put it in my givens. It asks what theorem can be used to show these 2 triangles are congruent, so we might as well just write out the proof. BD is a perpendicular bisector, which is given, and then BDA and BDC must be right angles. We know they're right angles because perpendicular lines form right angles. That's also known as the definition of perpendicular. Once we know they're 2 right angles, we know they're congruent to each other because the definition of right angles states all right angles equal 90 degrees. AD and CD are congruent to each other because of bisector. Bisector means it cuts it into two equal pieces, each half the original. And BD and BD are the same because of the reflexive property. Once we have that, we have our angle. We have a side here. We have a side here, which means side, angle, side. That's our SAS postulate. Not bad. Take a look at the lesson 4 problem set. Again, pause the video, try these out, and then I will show you the answers. All right. Here's the first question in the lesson 4 problem set. You can see the proof here. Nothing new here necessarily. We are trying to use this new ASA postulate though, and we're identifying ASA because there's an angle, here's another angle, and here's the side that is included. One thing that you should be noticing is that this prove statement is always going to be the last statement because once you prove this, you're done. Take a look at question number 2 and then number 3. I'll pause the video and then I will show you the answers. All right, one thing that you should be noticing is that whenever we have this symbol, which means perpendicular, or whenever we're talking about perpendicular lines, we have two different statements that we have to make in order. We have to first state that the two angles that are formed there are right angles because of the definition of perpendicular. And then we have to state that the two angles are perpendicular. In this case, it's actually SQT that is perpendicular. But anyway, it's very important to do these two steps because many times students will just jump to saying, oh, since this is perpendicular to this, then the two angles must be the same. You must say first they're right angles and then say that they are congruent to each other because of the definitions of perpendicular and right angles respectively. Everything else should be pretty straightforward by now. We're using reflexive property for the side that is congruent to itself, that shared side. We are using the definition of bisector because it says up here bisector. No big deal. All right, take a look at the question number 3. Try to do that, and I'll show you the answer in a moment. You'll see in this example, it asks you to prove that WMR is congruent to KRM. In this case, we don't have those triangles yet until we make this line. If you remember from 2 units ago, a line that we draw into a diagram to help us is called an auxiliary line. I can never pronounce that correctly. Anyway, this aux line here shows us WMR and KR. This should say W, I believe. Oh, look at that. It does say W. How about that? I guess I was just looking at it weird. Anyway, you can see angle M is congruent to angle K. Those are here and here. We know that these two angles are going to be congruent because of that alternate interior angles. We know that these two are parallel lines. We also know that tricky reflexive property means that WR is congruent to itself. And then WMR is congruent to KRW based on that AAS postulate. We know it's AAS because we have an angle here, and the non-included or a non-included side. AAS works here because this side is not between the two angles that we know. Taking a look at the last problem, the last page of this problem set, try this one by yourself and I will show you the correct answer. From here on, you can see that the proofs start to get a little trivial. We're doing the same thing over and over again, just with different diagrams. Here's proof number 5. You can see that we're using ASA postulate. And in proof number 6, it was a little bit strange, and I'll walk you through the reason why. It gave you these 4 givens, but there wasn't any straightforward way of getting the two triangles to be congruent. It's these two triangles on the sides, unless you knew that ABC was an isosceles triangle. Well, this angle and this angle, A and C, were congruent, which means it's an isosceles triangle. But then we knew that since it's isosceles, AB and CB must be the same because of the definition of isosceles. Once you have that, you have side, angle, side. So it's fairly straightforward to get those to be congruent. Taking a look at the last problem set, I'm going to show you the solutions in a moment. Leg Theorem is the 4th and final theorem that we learned about. Take a look at these correct answers. Pause the video, obviously, if you need help or if you need time to look at them, time to process. And now I'm going to show you the final page, which is the 4 proofs that are on the back. All right, these were the last 4 proofs. Feel free to pause the video, check your proofs over. One thing that you have to remember when you're using leg postulate is that we need to make sure that we state that they're right triangles. Otherwise, there is no hypotenuse, there is no leg. So please check over these proofs. Make sure that you know what you're doing with these because the Unit 5 quiz will be coming up before you know it. All right, this was the Unit 5 review for questions or for lessons 1 through 5. Hopefully this was helpful to you. Good luck studying.